All right, so this little section um, is about something that's specific to our AP Pre-Calculus test. We don't typically have free response questions regarding semi-log plots, but they're usually multiple choice. So we have kind of a short day of notes. I'll try to explain this the best that I can and look at what a semi-log plot is. All right. So if we're graphing exponential data, meaning the y values are growing fairly quickly without bound, then depending on how fast, what that base number is, how fast the numbers are growing, you can see the numbers grow pretty quickly to really large numbers. So the range goes from 2.5 to 23,000. And that can make patterns in the graph hard to see because we have to zoom out so far just to get the lowest point and the highest point in the same graph. So, for example, here's this graph where you can see, like, yeah, it kind of looks like almost a flat line of data for the first 3 points, and then a little bit higher at 5, and then we can see some growth here. But there might be more information or more variation in these first few points. If we didn't have the data set, it would be really hard to tell what was going on here. So sometimes we want to change the scale of this graph so that we're still looking at the data, but we're seeing if there are any other relationships between the inputs and the outputs. So we're going to use log properties to see what happens to a generic exponential equation if we start taking the log of both sides. So that means just like I can square root both sides, I can log both sides, but I want to change f of x to y just to make the work a little bit easier to show. All right. So if I log both sides, and I could ln both sides if I wanted as well, that would be the log of y equals the log of a times b to the x. And then I can work on this side a little bit. I can say, well, this expands out. This is the log of a plus the log of b to the x. And we know with our expansion rules that anytime we have an exponent inside of a logarithm, we can multiply that out in front. So this is the log of a plus x times the log of b equals the log of y. And what did this do for us? It's kind of hard to look at this and see, like, okay, so how is this any better? What this shows me is that the log of the y values is equal to some sort of linear equation. I know this is linear because it just has an x to the first. The y-intercept is the log of a. And let me switch this around. Log of b is the slope multiplied by x to the first. So why is that important? Because if we look at a linear relationship, we can look at things like slope, and we can see all of the data points on a much smaller window. So the idea is this. If I change the original data table so that I'm comparing the original x values to not the original y values, but the log of all the y values. So you can see it's log of 2.5, log of 12.5. That makes all of these numbers much smaller. Now, instead of the range going from 2.5 to 23,000, it ranges from 0.3979 to 4.37. And I can look at this graph and say, oh yeah, this is a roughly linear relationship. So there's a roughly linear relationship, not between x and y, but between x and the log of y. So anytime you have an exponential function, you should see a roughly linear relationship between x and log x. And the same thing would be true if I did the natural log of y. It won't be perfectly linear because this data wasn't perfectly exponential, but we have something very close. All right, so let's take a look at another way to look at this. Notice that the scale has changed. So here the scale was, for the y's, was 0 to 4 because our numbers went from 0.39 to 4.3. So here, same idea, but the scale is now back to like, this has 10 to the first and then 10 squared. So you're going from 0 to 10. That's an increase of 10. Now you're going from 10 to 100. Well, that is an increase of 90, right? And then 100 to 1,000. So even though it looks like you're increasing by the same amount, you're not really. If I go back to this graph, this point here represented 2 and then the log of 2.5. And on this graph, we're back to this representing the point 2 and 2.5. Because see where this point falls? It falls between 0 and 10. And like this point right here, it's just above 10 because it represents the point 3, 12.5. Whereas this one represented 3 and the log of 12.5, which was just a little bit over 1. All right, so when you're picking out semi-log plots, you kind of want to pay attention to which one has the correct scale and which one matches the data set. So what am I looking for when I'm looking at problems that kind of change the scale for this? So one thing I didn't give you a very good example of is like a semi-log plot. Sometimes they change the scale so that it doesn't look like this. Honestly, I'm just going to let me Google a semi-log plot for you to look at. Let's see. So you might see something like this, where, of course, it's going to be, let me get to this graph. Okay. Ooh, it's hard to see on there. Okay. So here they have the scale with like different variations. So see how it's like really scrunched in together here and then really far out here. So sometimes they, instead of keeping the scale like 0 to 1, then it goes 1 to 10, then it goes 10 to 20. So you can see like this is jumping. They're sort of scrunching the lines in here. It's really hard to see on the green graph. But when I'm in AP Classroom and I'm given multiple choice questions and they're just like, which one is the semi-log plot of this set of data? I'm just looking for the one that has like a scrunched down, for lack of a better word, scale. Oh, here's one where you can see it a little better. So see how it goes from 1 to 10 to 100, just like ours did? But instead of in the notes, instead of having just nice boxes that are the same width, it starts off with like a wide box and then it scrunches down to get smaller to show that like, yeah, we are making a jump from 10 to 100. So these changes are sort of condensing as you get closer to the higher number. All right, so sorry if that's kind of confusing, but when you're in AP Classroom, you're just looking for the y-axis that has powers of 10 probably, but it might have lots of variation in these lines, like something like this in between all of these. All right, practice with some AP style problems. So these are just kind of preview of the types of problems we might see in AP Classroom. So which table provides evidence that f of x is exponential if y is equal to f of x? So if exponential, there are two scenarios. If it's an xy table, then I should see a common ratio in the ratio in the y values here. Like I'm always multiplying by 2 or I'm always multiplying by 1/2, something like that. If it's x and log or ln of y, then I should see a common difference or a linear relationship in the y values. So let's take a look. X and y, this is not an exponential function. You're adding 4 every time. That's a common difference. So this is not exponential. In fact, this is just a linear relationship between x and y. Now, if I have x and ln y, I am looking for a linear relationship if I want it to be exponential. So let's see. This one, add 10, add 20, add 40. That's not linear. This is doubling. This is times 2, times 2, times 2. So this is not exponential. there's an exponential relationship between x and ln y, but that's not what it's asking. It's asking if x and y have an exponential relationship. Okay, so what if we change this then? So this is back to x and y. Here's where we're saying times 2, times 2, times 2. So this is exponential because there's a common ratio, r equals 2. And then back here, I have x and ln y. So if I'm comparing these, I want to see a linear relationship or a common difference. So here, 10 to 14 is plus 4, 14 to 18 is plus 4, 18 to 22 is plus 4. So this means that x and ln y are linear. And that means that x and y, x and y are exponential. And that is what the question is asking. X and y are exponential. And on this one too, x and y have an exponential relationship. In a semi-log plot, which set of functions would appear as parallel lines? I think I have a typo in this. There shouldn't be a plus 2 on this one, and there shouldn't be a plus 4 on this one. So in a semi-log plot, what are we looking for here? So we would need to say, well, I would be logging the y values just like I did at the start. So say this is y equals 3 to the x, and this one is going to be y equals 1/3 to the x. So if I have different bases, will I get the same slope if I log the y values? So log both sides. That would be log of y equals log of 3 to the x. And this would be log of y equals x times log of 3. So the slope in the first equation is log of 3. If you're doing this one and you log both sides, get the log of 1/3 to the x. That becomes x log of 1/3. So in this equation, the slope, the number that's getting multiplied by x, is the log of 1/3, and that's not the same as the log of 3. So these would not be parallel lines. And if I think about this, really, this is just saying, hey, yeah, if you have the same base number, then you're going to have the same slope here. Take a look at this one. We have the same base number, and even if there's a 3 out in front, let's do the same thing. Y equals 5 to the x. Y equals 3 times 5 to the x. Log of y equals log of 5 to the x. Log of y equals x times log of 5. So the slope in this equation is log of 5. In this one, log of y would equal log of 3 times 5 to the x. Expand that out. That's log of 3 plus x log of 5. This is still a linear equation with a slope of 5. The slope is the number that's being multiplied by x. This is the y-intercept, which doesn't matter. So yeah, these are parallel lines. If I were to graph each of these log equations, if I were to graph each of these expressions, they would look like parallel lines. Okay, given the table, write the exponential function that fits without using a calculator. So if I could use a calculator, I could just like try to do regression somehow. But pay attention to this. This says log base 2 of f of x is equal to 4 or 6 or 8. So the first thing I want to look at is like, I'm trying to write an exponential function like y equals some a times some b to the x. And a and b are related to the slope of a linear equation, right? So in a semi-log plot, it's like I can log both sides any way I want. So I could log base 2. Log base 2 of y equals the log base 2 of a times b to the x. So the log base 2 of y will equal the log base 2 of a plus the log base 2 of b to the x. Let's put the x out here. Remember, this is the slope, and this is the y-intercept. And if I have this graph, I can get the slope and the y-intercept from the, not from the graph, sorry, from the table. So the table shows me the y-intercept. The y-intercept is 0, 4. So that number is 4. And the slope is the slope between any 2 points here. 6 minus 4 over 1 minus 0. That's a slope of 2. Okay, so that tells me that the log base 2 of a is equal to 4. So what is a? 2 to the 4th equals a. So a is 16. And what about this one? The log base 2 of b is equal to 2. So exponential form, 2 to the 2nd is equal to b. So b is 4. So my exponential equation then is y equals 16 times 4 to the x power. You will see all of these problems or something similar to these problems in our next AP Classroom assignment. So I just wanted to practice something a little bit out of the box here. We know our AP questions are a little bit out there. So we'll just see how this goes tomorrow. Please let me know if you have any questions.